What happened to 3I Atlas on September 7th during the lunar eclipse changes everything we thought we knew about this interstellar visitor. The comet that astronomers confirmed was producing virtually no diatomic carbon just 1 month ago has suddenly exploded into brilliant green fluorescence, displaying molecules that spectroscopic analysis said weren't there. But that's just the beginning of a chain of discoveries that are rewriting cometary physics in real time. While you were tracking 3I Atlas's approach to perihelion, Hubble revealed something that has never been observed in the history of astronomy: a sunward extension of scattered light that stretches 10 times longer than the comet's width, pointing directly toward the sun instead of following conventional radiation pressure physics. And here's what's driving the headlines that are confusing even seasoned space enthusiasts. The viral claims about a second massive comet supposedly racing toward us aren't describing a new discovery at all. They're conflating Bernardinelli-Bernstein's slow approach with 3I Atlas's current passage, creating a perfect storm of misinformation that's spreading faster than the actual science. Tonight, we're diving deep into the latest data that's emerged just this week. You'll discover why Atlas's cyanide production is spiking at rates that follow a power law with an exponent of 9 mathematical behavior that suggests chemistry unlike anything we've seen in solar system comets. We'll explore how TESS observations revealed the comet was already active in March, when it was beyond Jupiter's orbit, activity that challenges everything we understand about volatile sublimation thresholds. Most importantly, you'll learn why Avi Loeb's analysis of the Hubble images reveals geometric corrections that make this sunward phenomenon even more extreme than initially reported, and why this single observation might force us to reconsider fundamental assumptions about how interstellar objects behave when they encounter stellar radiation. The data coming in from the Mars encounter in just 2 weeks will either confirm that we're witnessing exotic physics, or reveal that Atlas operates by rules we haven't discovered yet. But first, we need to understand exactly what that green transformation tells us about chemistry that might only exist in materials forged around alien stars. Before we begin, I'd love for you to tap that like and subscribe button, but only if you truly enjoy these scientific deep dives designed to help you relax, focus, or drift off to sleep. You can also give this video an extra boost with the new hype feature just below. In the comments, let me know where you're listening from, what time it is there, and the strangest scientific phenomenon that fascinates you. I'll be reading and replying to many of them, and who knows, your idea might inspire our next video. Now, back to our green glowing visitor and the mystery that's capturing headlines worldwide. The impossible green transformation. For months, every spectroscopic analysis of Atlas showed a distinctly reddish character, consistent with what we'd expect from ancient interstellar material. The colour signature told a story of primordial compounds, perhaps unchanged for billions of years as this cosmic time capsule drifted through the void between stars. Then, on September 7th, during the lunar eclipse that darkened our skies, something switched on. Yeager and Raymond's photographs revealed an unmistakable emerald glow emanating from our interstellar guest. This wasn't subtle. This wasn't a trick of processing or atmospheric effects. The transformation from red to green represents a fundamental change in the chemical processes occurring within Atlas's coma, the glowing envelope of gas and dust surrounding its nucleus. Harvard's Avi Loeb, whose unconventional theories about interstellar objects have sparked both intrigue and controversy, immediately noted the significance. The green coloration in comets typically results from diatomic carbon molecules, carbon atoms bonded in pairs that fluoresce under solar radiation. But here's where the mystery deepens beyond comfortable explanations. Just 1 month earlier, astronomers at Kitt Peak Observatory had specifically searched for carbon chain molecules, including diatomic carbon, in Atlas's spectrum. They found virtually none. The absence was so pronounced that it ruled out diatomic carbon as a significant component of the comet's composition. Yet now, barely weeks later, the object glows green with what appears to be the unmistakable signature of those very same molecules. What changed? Several possibilities emerge from the shadows of our current understanding. Perhaps the sun's increasing heat has penetrated deeper layers of the comet's nucleus, sublimating previously hidden reserves of carbon compounds locked beneath the surface. Perhaps we're witnessing the activation of chemical processes that don't occur in our solar system's native comets, reactions that only unfold under the specific conditions present in this alien visitor. Or perhaps, as some researchers quietly suggest, the green glow isn't coming from diatomic carbon at all, but from some other molecule entirely, one that we haven't yet identified or understood. This possibility opens doors to chemistry that might be common in the star system where Atlas originated, but entirely foreign to our cosmic neighbourhood. The brightening beyond predictions. While the colour transformation captures headlines, an equally significant development has been unfolding in the comet's brightness behaviour. As of mid-September, Atlas is outperforming every prediction, brightening faster than any model suggested possible. The Comet Observation Database, maintained by CRNI-VERH Observatory, shows a clear departure from expected behaviour. Initially discovered at magnitude 17, barely visible to the most sensitive telescopes, Atlas has surged to magnitudes 12 through 14 by September's end. The trajectory suggests it could reach magnitude 12 by late October, making it the brightest interstellar object ever observed, though still requiring telescopic assistance for human eyes. This rapid brightening indicates massive increases in outgassing activity. Dr. Adina Feinstein's team at Michigan State University, analysing pre-discovery images from NASA's Transiting Exoplanet Survey satellite, found evidence that this acceleration has been building since March, when Atlas was still beyond Jupiter's orbit. The comet has been active at distances where our solar system's comets remain completely dormant. The implications stretch beyond simple sublimation rates. University of Maryland's Kwanzi Ye notes that Atlas follows a brightening pattern more consistent with dynamically old comets from our own Oort cloud, objects that have made multiple passes through the inner solar system. Yet this interpretation presents a paradox. How does an interstellar visitor, on its first encounter with our Sun, behave like a comet with extensive solar exposure history? The sunward anomaly. Perhaps the most perplexing discovery emerged from careful analysis of Hubble Space Telescope images taken on July 21st. Avi Loeb and Eric Quito's investigation revealed something unprecedented in cometary science, an extended glow that stretches not away from the Sun, as traditional comet tails do, but directly toward our star. This sunward extension, which they term an anti-tail, appears to be 10 times longer than the comet's width when corrected for our viewing angle. No comet in recorded history has displayed this behaviour. Traditional comet tails form when solar wind and radiation pressure push material away from the nucleus. The physics of an anti-tail pointing sunward challenges our fundamental understanding of how these objects interact with stellar environments. The implications ripple through multiple fields of study. If Atlas is generating some form of directed outgassing toward the Sun, the mechanism remains completely mysterious. Solar heating should create symmetric expansion or preferential outgassing from the Sun-facing hemisphere, not the focused beam-like structure observed in Hubble's images. Some researchers have quietly begun investigating whether Atlas might be exhibiting behaviour inconsistent with a purely natural object. The alignment of its trajectory with the ecliptic plane, the unusual chemical composition, the anomalous brightening, the colour transformation, and now the anti-tail create a pattern of characteristics that stretches coincidence to uncomfortable limits. The chemical enigma deepens. The Very Large Telescope's observations on August 25th revealed another layer of mystery. Both cyanide and nickel production from Atlas increase dramatically as the comet approaches the Sun, following a power law with an exponent of approximately 9. This represents one of the steepest production rate increases ever measured in cometary science. More intriguingly, the nickel appears without accompanying iron, a combination that occurs naturally in only a few specific contexts. Industrial nickel alloys produced through human metallurgy often feature this nickel without iron signature. While this doesn't necessarily imply artificial origin, it adds another unusual characteristic to an already anomalous object. The The Webb Space Telescope's analysis revealed that Atlas's coma composition is dominated by carbon dioxide at 87% by mass, with carbon monoxide comprising 9% and water accounting for most of the remaining 4%. This ratio differs significantly from both previously observed interstellar comets and typical solar system comets, suggesting formation conditions unlike anything in our immediate cosmic vicinity. The rapid increase in cyanide production as Atlas approaches the Sun raises questions about the stability of organic compounds within the nucleus. Cyanide, while naturally occurring in comets, typically appears at relatively constant rates. The exponential increase observed in Atlas suggests either unusual chemistry or structural characteristics that we don't yet understand. The Mars Encounter. October 3rd marks a crucial milestone in Atlas's journey through our solar system. The comet will make its closest approach to Mars, passing within 28 million kilometers of the red planet. This presents an unprecedented opportunity for detailed observation using spacecraft designed for Martian exploration. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter will turn their instruments toward the interstellar visitor, attempting spectroscopic analysis and imaging despite the comet appearing as less than a single pixel in their cameras. The high-resolution stereo camera and color and stereo surface imaging system, typically focused on Martian landscapes, will instead peer into deep space seeking clues about alien chemistry. More significantly, these observations will occur during Atlas's most active period, as solar heating drives maximum outgassing rates. The spectrometers aboard both missions may detect additional chemical signatures that Earth-based telescopes cannot resolve, potentially solving the mystery of the green transformation or revealing new complexities in the comet's composition. The timing also allows comparison with NASA's Perseverance rover and Curiosity, both of which carry instruments capable of atmospheric analysis. While the rover's primary mission focuses on Martian geology and astrobiology, the atmospheric monitoring equipment might detect any particles or gases released by Atlas as it passes through the neighborhood. The Jupiter connection. November brings another observational opportunity as ESA's Jupiter Icy Moons Explorer, currently en route to the Jovian system, attempts observations of Atlas using multiple instruments. The spacecraft's position will provide a unique vantage point for studying the comet's behavior as it begins its outward journey from perihelion. The spacecraft carries ultraviolet spectrographs designed to analyze the chemical composition of Jupiter's moons and magnetosphere. These instruments may detect spectral lines from Atlas that are impossible to observe from Earth due to atmospheric interference, potentially revealing the source of the mysterious green glow or identifying additional chemical signatures. Coordination with NASA's Europa Clipper mission offers the possibility of simultaneous observations from multiple positions, creating a three-dimensional view of Atlas's coma structure and activity patterns. The twin ultraviolet spectrographs on both spacecraft represent the most advanced instruments available for detailed chemical analysis of the comet during its most active phase. However, technical challenges complicate these observations. Jupiter Icy Moons Explorer currently uses its main antenna as a heat shield while passing close to the Sun, limiting communication to slower data rates through backup systems. Results from any Atlas observations may not reach Earth until February 2026, months after the comet has passed perihelion and begun fading. The second comet, Misconception. Amid the excitement surrounding Atlas, social media and certain news outlets have begun circulating claims about a second, even more massive comet entering our solar system. This narrative appears to stem from confusion between Atlas and Comet Bernardinelli-Bernstein, officially designated C 2014 UN 271. Comet Bernardinelli. Bernstein is indeed enormous, with a nucleus diameter of approximately 140 kilometers, making it roughly 100 times larger than typical comets. However, this giant is not a new arrival or a second interstellar visitor. Discovered in 2021 through analysis of archived images dating back to 2014, Bernardinelli-Bernstein has been slowly approaching our inner solar system for years. The confusion intensifies because Bernardinelli-Bernstein will reach its closest approach to the Sun in January 2031, still more than 5 years away. At its nearest point, it will remain beyond Saturn's orbit, never entering the inner solar system where Earth and Mars orbit. While genuinely massive and scientifically fascinating, it poses no threat and won't become visible to amateur astronomers. Recent observations have detected carbon monoxide jets erupting from Bernardinelli-Bernstein's nucleus, confirming its cometary nature and indicating increasing activity as solar heating penetrates its massive bulk. The Atacama Large Millimeter Array has mapped these jets, revealing asymmetric outgassing that suggests complex nuclear structure and rotation. The hype surrounding a second massive comet appears to result from misunderstanding the timeline and nature of Bernardinelli-Bernstein's approach. Social media algorithms, optimized for engagement rather than accuracy, have amplified these misconceptions, creating viral content that conflates multiple distinct astronomical objects and events. The trajectory mystery. Recent analysis by Xavier Perez-Couto's team at the University of A Coruña has traced Atlas's path backward through 10 million years of galactic motion, attempting to identify its origin star system. The results prove both fascinating and frustrating. No single star system shows clear evidence of ejecting Atlas within the time frame suggested by its trajectory. This absence of an obvious parent system raises questions about the comet's true age and origin. If Atlas spent significantly longer than 10 million years wandering interstellar space, its point of origin becomes increasingly difficult to determine. Gravitational interactions with multiple star systems could have altered its trajectory numerous times, obscuring its original path. Alternatively, Atlas might originate from the galaxy's thick disk, a population of older stars distinct from the thin disk where our Sun resides. Dr. James Davenport notes that the comet's galactic trajectory aligns with thick disk kinematics, suggesting formation around ancient metal-poor stars that existed when our galaxy was young. This possibility makes Atlas not just an interstellar visitor, but potentially a relic from cosmic dawn, carrying chemical signatures from stellar environments that no longer exist. The unusual composition, including the dominance of carbon dioxide over water, might reflect formation conditions around stars with different metallicity than our Sun's neighbourhood. The TESS discovery. Dr. Feinstein's analysis of transiting exoplanet survey satellite images revealed Atlas in photographs taken during May 2025, 2 months before its official discovery. These pre-discovery observations show the comet already displaying significant activity at distances where solar system comets remain completely dormant. The TESS images required sophisticated processing to extract the faint comet signal from background stars and instrumental noise. By combining multiple exposures and filtering starlight, Feinstein's team revealed a fuzzy object showing clear signs of coma development. This confirms that Atlas began outgassing at approximately 6 astronomical units from the Sun, twice the distance where Jupiter orbits. Such early activity suggests either unusual volatile composition or structural characteristics that make Atlas more sensitive to solar heating than typical comets. The Zwicky Transient Facility data extends observations back to March, when the comet was beyond Jupiter's orbit but already showing detectable brightness variations consistent with active outgassing. This extended activity timeline provides crucial data for understanding Atlas's behavior as it approaches perihelion. The brightening rate follows a power law with an exponent of -3.8, significantly steeper than the interstellar comet Borisov, but consistent with dynamically old comets from our own solar system. The green chemistry puzzle. The September transformation to green emission presents one of the most intriguing mysteries in modern cometary science. Several mechanisms could potentially explain this sudden appearance of what appears to be diatomic carbon fluorescence, each with different implications for our understanding of Atlas's nature. Solar heating might have penetrated through surface layers that previously shielded subsurface carbon compounds from sublimation. As Atlas approaches perihelion, increasing temperatures could reach deeper into the nucleus, accessing reservoirs of carbon-rich material that remained frozen during the comet's interstellar journey. Alternatively, the green glow might result from chemical reactions between previously separated compounds, now brought together by the disruption of the nucleus structure. Solar heating doesn't just sublimate ices, it can fracture the porous structure of cometary nuclei, create new pathways for volatile transport and mixing. A third possibility involves molecules other than diatomic carbon producing green fluorescence under specific excitation conditions. While diatomic carbon is the most common source of green cometary emission, other compounds can produce similar spectral signatures under particular circumstances. The unusual chemistry of Atlas might involve fluorescent molecules not typically found in solar system comets. The timing of the transformation, coinciding with increased solar heating as Atlas approaches perihelion, supports thermal activation of previously dormant chemical processes. However, the suddenness of the change suggests a threshold effect rather than gradual activation, implying complex chemistry or structural changes within the nucleus. The polarization anomaly. Recent polarimetric observations have revealed another unusual characteristic of Atlas. The comet displays an extremely deep negative polarization of -2.77% with a low inversion angle of 6.41 degrees. These values place Atlas outside the normal range for both solar system comets and the previously observed interstellar comets. Polarization measurements reveal information about the size, shape, and composition of dust particles in the coma. The unusual polarization signature suggests that Atlas ejects dust with characteristics significantly different from typical cometary material. This could indicate unusual composition, different formation conditions, or structural modifications during its interstellar journey. The negative polarization at small phase angles combined with the low inversion angle suggests dust grains with high albedo and unusual optical properties. Such characteristics might result from coating with organic compounds, crystalline structures formed during slow cooling in interstellar space, or composition dominated by materials rare in our solar system. These polarimetric measurements provide independent confirmation that Atlas differs fundamentally from both solar system comets and the other known interstellar visitors. The combination of unusual chemistry, anomalous brightness behavior, mysterious green transformation, and distinctive polarization creates a profile unlike any previously studied object. The nuclear composition question. Hubble Space Telescope observations have progressively refined estimates of Atlas's nuclear size, with recent analysis suggesting a diameter between 440 meters and 5.6 kilometers. This range spans nearly an order of magnitude, reflecting the difficulty of separating nuclear brightness from surrounding coma emission. The uncertainty in nuclear size directly affects calculations of mass, density, and composition. A smaller nucleus would require higher activity rates to produce the observed coma brightness, suggesting either unusual volatile composition or structural characteristics that enhance outgassing efficiency. A larger nucleus could harbour greater reserves of exotic ices while maintaining normal activity rates. Spectroscopic analysis indicates that the nucleus itself might be unusually dark, reflecting only a small fraction of incident sunlight. This low albedo could result from organic compounds formed during irradiation in interstellar space, carbon-rich composition reflecting formation conditions around different types of stars, or surface modifications during the comet's long journey between star systems. The combination of uncertain size and low reflectivity complicates efforts to understand Atlas's internal structure and composition. Advanced thermal modelling, incorporating data from multiple wavelengths and observation geometries, may eventually resolve these ambiguities as the comet approaches maximum activity near perihelion. The activity profile. Atlas displays an activity profile unlike any previously observed comet, beginning significant outgassing at distances where solar system comets remain completely dormant. This early activation suggests composition dominated by highly volatile materials that sublimate at lower temperatures than water ice. The steep brightening curve, with a power law exponent of -3.8, indicates rapidly increasing activity as the comet approaches the Sun. This behavior resembles dynamically old comets from our own Oort cloud, objects that have made multiple passages through the inner solar system and developed enhanced volatile transport networks. However, Atlas is supposedly making its first approach to any star system since being ejected from its parent system millions or billions of years ago. The contradiction between fresh interstellar status and old comet behavior suggests either unusual formation conditions or modifications during its interstellar journey that created characteristics normally associated with solar exposure. Recent observations show that both dust and gas production rates increase exponentially with decreasing solar distance, following power laws with exponents approaching 9 for certain chemical species. This extreme sensitivity to solar heating implies either very shallow subsurface volatile reservoirs or enhanced heat transfer mechanisms within the nucleus. The spacecraft observations. Multiple spacecraft throughout the solar system will attempt observations of Atlas during its closest approach to the Sun, providing unprecedented multi-angle coverage of an interstellar visitor. These observations span different electromagnetic wavelengths and observational geometries, creating the most comprehensive dataset ever collected for an object of this type. NASA's Parker Solar Probe, designed to study the Sun's corona, will observe Atlas using its Wide-Field Imager for Solar Probe instrument during late September through early November. This timing covers the comet's perihelion passage and offers views from closer to the Sun than any other observatory can achieve. The Lucy mission, en route to study Jupiter's Trojan asteroids, may capture images of Atlas from its unique position in the outer solar system. Similarly, NASA's Psyche mission, travelling toward the metal-rich asteroid 16 Psyche, passed close to Atlas on September 4th, though no images have yet been released publicly. The most intriguing observations may come from ESA's Hera mission, launched to study the aftermath of NASA's DART impact on asteroid Didymos. Hera's instruments, designed for detailed surface mapping and composition analysis, could provide unprecedented views of Atlas's nucleus structure during its approach phase. The communication challenge. Several planned observations face significant technical challenges related to spacecraft positioning and communication constraints. Jupiter Icy Moons Explorer, potentially offering the best views of Atlas during peak activity, currently cannot transmit data at normal rates due to its proximity to the Sun, requiring antenna shielding. The spacecraft's main high-gain antenna serves as a heat shield during solar close approach, forcing communication through smaller backup antennas with severely limited bandwidth. This constraint means that any Atlas observations may not reach Earth until February 2026, months after the comet has passed perihelion and begun fading. Europa Clipper faces similar challenges as it travels through the inner solar system toward its eventual Jupiter destination. The spacecraft's instruments are optimized for icy moon analysis rather than cometary observation, though its ultraviolet spectrographs may detect spectral signatures invisible to Earth-based telescopes. Coordination between multiple spacecraft observations requires precise timing and data correlation to maximize scientific return. The challenges of interplanetary communication, combined with the brief observational windows as Atlas races through the inner solar system, demand careful planning and realistic expectations for data acquisition. The theoretical implications. The accumulating anomalies associated with Atlas challenge several fundamental assumptions about interstellar objects and cometary science. The combination of unusual trajectory alignment, distinctive chemical composition, anomalous brightness behavior, mysterious color transformation, and unprecedented sunward glow creates a pattern that defies simple explanation. Some researchers have begun exploring whether Atlas represents a new class of interstellar object, perhaps formed under conditions not present in our solar system's region of the galaxy. The dominance of carbon dioxide over water, the early activation of outgassing, and the unusual nuclear composition might reflect formation around different types of stars with distinct chemical environments. The possibility that Atlas originates from the galaxy's thick disk opens questions about stellar nuclear synthesis in early galactic history. If this interpretation proves correct, the comet carries chemical signatures from stellar environments that existed when our galaxy was young, providing direct samples of ancient stellar processing. Alternative explanations range from conventional but unusual natural processes to scenarios that stretch the boundaries of current scientific understanding. The alignment with the ecliptic plane, combined with the other anomalies, has prompted some researchers to investigate whether Atlas might represent something other than a typical comet. The October climax. As October progresses toward the 13th, Atlas will reach its closest approach to the Sun, marking the climax of its journey through our solar system. This perihelion passage, occurring at approximately 1.4 astronomical units, places the comet between the orbits of Earth and Mars at its moment of maximum solar heating. The weeks surrounding perihelion represent the peak opportunity for scientific observation, as outgassing rates reach maximum levels, and the comet's true nature becomes most apparent. However, the comet's position relative to Earth during this crucial period places it on the opposite side of the Sun, making ground-based observations extremely challenging. Solar conjunction, when Atlas appears close to the Sun in Earth's sky, will render the comet unobservable from our planet during its most active phase. This frustrating timing means that the most dramatic developments in Atlas's evolution may occur beyond the reach of our most powerful Earth-based telescopes. Space-based observatories, including those aboard Mars orbiters and the various spacecraft scattered throughout the solar system, become crucial for maintaining observational coverage during this critical period. The Parker Solar Probe, specifically designed to operate in the harsh environment near the Sun, may provide the only detailed observations of Atlas at perihelion. The outbound journey. Following perihelion passage, Atlas will begin its long journey back to interstellar space, never to return to our solar system. The outbound observations, beginning in early November as the comet emerges from solar conjunction, will reveal how the intense solar heating has modified its nucleus and activity patterns. Many comets experience dramatic changes during perihelion passage, with some fragmenting under thermal stress while others develop new outgassing patterns that persist for months or years. The behavior of Atlas during its outbound journey will provide crucial clues about its internal structure and composition. The fading phase of Atlas's visit offers opportunities to study how an interstellar object responds to intense solar heating and whether the experience creates lasting modifications. Changes in brightness, spectral characteristics, or coma structure during the outbound journey could reveal how thermal cycling affects materials formed in other star systems. By early 2026, Atlas will have faded beyond the reach of most telescopes, returning to the interstellar medium, carrying whatever modifications its solar encounter has produced. The comet will spend the next several million years crossing the void between stars, potentially carrying Earth-based contamination or solar system signatures to distant regions of our galaxy. The long-term questions. The brief visit of Atlas raises profound questions about the frequency and nature of interstellar visitors to our solar system. If such objects pass through regularly, as some models suggest, our solar system exists within a constant stream of material from other star systems, creating ongoing opportunities for chemical and potentially biological exchange. The unusual characteristics of Atlas suggest that interstellar objects may be far more diverse than the small sample we've observed indicates. Each visitor carries unique signatures of its formation environment, potentially revealing information about stellar conditions throughout our galaxy's history and various regions of space. Future surveys, including the Vera Rubin Observatory scheduled to begin operations soon, will dramatically increase our detection rate for interstellar objects. The observatory's wide field coverage and sensitive instrumentation may reveal dozens of visitors like Atlas, creating a substantial database for comparative analysis. The European Space Agency's Comet Interceptor mission, designed specifically to study pristine comets and potentially interstellar visitors, represents the next generation of exploration tools for these objects. Unlike sample return missions that require years of advanced planning, Comet Interceptor will remain on standby, ready to investigate any suitable target that appears with sufficient warning. The detection revolution. The discovery of Atlas demonstrates how modern survey capabilities have revolutionized our ability to detect and study interstellar objects. The network of Atlas telescopes, combined with archives from the Zwicky Transient Facility and other surveys, creates comprehensive coverage that ensures few bright interstellar visitors will escape detection. Artificial intelligence and machine learning algorithms now scan millions of astronomical images automatically, identifying moving objects and anomalous signatures that might indicate interstellar origin. These systems can process observational data faster than human astronomers, enabling rapid follow-up observations while objects remain accessible. The integration of space-based and ground-based observatories creates multiple independent detection paths, with instruments like the Transiting Exoplanet Survey satellite providing additional coverage that fills gaps in ground-based monitoring. This redundancy ensures that interstellar objects like Atlas can be detected and studied even when initially too faint for any single survey. Advanced data sharing protocols allow rapid dissemination of discovery information to observatories worldwide, enabling coordinated follow-up observations that maximize scientific return. The Minor Planet Center's automated notification systems ensure that significant discoveries reach the global, astronomical community within hours of initial detection. The Chemical Database. Each interstellar visitor contributes unique data to our growing database of chemical compositions from other star systems. The unusual carbon dioxide dominance in Atlas, combined with distinctive nickel signatures and absence of expected iron, provides information about stellar nucleosynthesis and planetary formation processes in different galactic environments. Comparison between Atlas, the previous visitors Oumuamua and Borisov, and future interstellar objects will reveal whether common formation processes occur throughout our galaxy or whether each star system produces distinctive chemical signatures. The diversity observed so far suggests significant variation in stellar environments and planetary system evolution. Spectroscopic databases compiled from multiple interstellar visitors may eventually enable determination of object origins through chemical fingerprinting. Different stellar populations throughout our galaxy should produce characteristic element ratios and molecular compositions that serve as signatures of their formation environments. The accumulating data also provides crucial input for theoretical models of galactic chemical evolution, stellar nucleosynthesis, and planetary system formation. Direct samples from other star systems offer unprecedented opportunities to test models that previously relied entirely on astronomical observations and laboratory experiments. The contamination question. As Atlas passes through our solar system, it potentially acquires contamination from solar wind particles, interplanetary dust, and even traces of Earth's atmosphere that escape to space. This acquired material will accompany the comet back to interstellar space, carrying chemical signatures of our solar system to distant regions of the galaxy. The possibility of biological contamination, while extremely remote, raises fascinating questions about interstellar transfer of organic material. Earth's upper atmosphere contains microorganisms that might theoretically survive, transfer to passing interstellar objects, though the extreme conditions of space make such survival highly unlikely. More significantly, Atlas may carry industrial signatures from human activity, including isotopic ratios characteristic of nuclear technology and synthetic compounds produced only by technological civilizations. If the comet eventually encounters other star systems, these signatures could serve as evidence of technological activity in our solar system. The reverse possibility, that Atlas carries signatures from its origin system, drives much current research into the comet's composition and characteristics. Any unusual elements, isotopic ratios, or organic compounds could provide direct evidence of conditions around other stars or even biological processes in distant planetary systems. The future visitors. Statistical models suggest that objects like Atlas pass through our solar system regularly, perhaps several times per decade, though most remain too faint for detection with current technology. The Vera Rubin Observatory and other next-generation surveys will dramatically increase our detection sensitivity, revealing a constant stream of interstellar visitors. Each new detection will add to our understanding of galactic populations, stellar system characteristics, and the frequency of planetary formation throughout our cosmic neighborhood. The accumulating data may reveal patterns in visitor characteristics that reflect the structure and evolution of our galaxy's stellar populations. Advanced mission concepts under development include rapid response spacecraft, capable of intercepting interstellar objects with minimal advance warning. These missions would carry sophisticated analytical instruments for detailed in situ studies impossible from ground-based observations. The European Space Agency's Comet interceptor represents the first such mission, designed to rendezvous with a pristine comet or interstellar object for detailed investigation. Future missions may include sample return capabilities, bringing material from other star systems directly to Earth-based laboratories for comprehensive analysis. The technology evolution. The study of Atlas demonstrates how rapidly evolving technology enhances our capability to investigate cosmic visitors. Advanced spectroscopic techniques, machine learning algorithms for data analysis, and coordinated multi-wavelength observations create research capabilities that surpass those available for previous interstellar objects. Future technological developments will further expand our investigative tools. Next-generation space telescopes, including the James Webb Space Telescope's successors, will provide unprecedented spectroscopic resolution for studying faint interstellar objects. Advanced coronagraph systems may enable detailed observations even when objects appear close to the Sun. Artificial intelligence systems trained on vast databases of astronomical observations will identify subtle patterns and anomalies that human researchers might miss. These systems may detect evidence of unusual composition, artificial origin, or exotic physics in ways that complement traditional analytical approaches. The integration of quantum sensing technologies, advanced materials science, and sophisticated computational modeling creates new possibilities for understanding objects that spend only brief periods within observational range. These tools may reveal secrets of interstellar visitors that remain hidden with current technology. The philosophical implications. The passage of Atlas through our solar system raises profound questions about our place in the galaxy and the nature of the cosmic environment surrounding Earth. We exist within a dynamic system where material constantly flows between star systems, creating connections across vast distances and timescales. The possibility that some interstellar visitors might be artificially created objects, while scientifically controversial, forces consideration of how we might recognize evidence of other technological civilizations. The accumulating anomalies associated with Atlas, while probably natural in origin, illustrate the challenges of distinguishing artificial from natural phenomena. The chemical diversity observed in interstellar objects suggests that our solar system represents just one example among countless variations throughout the galaxy. The conditions that enabled life on Earth may be common, rare, or unique, depending on how frequently the chemical ingredients for biology appear in other stellar systems. The brief windows available for studying interstellar visitors emphasize both our current limitations and the vast scope of cosmic phenomena beyond our detailed investigation. Each visitor carries information about distant regions of space and time, but our fleeting opportunities for investigation capture only fragments of these cosmic stories. The observational networks. The international collaboration required to study Atlas demonstrates how modern astronomy transcends national boundaries and institutional limitations. Observatories across 6 continents coordinate observations, sharing data through sophisticated networks that enable real-time analysis of rapidly evolving phenomena. The Atlas survey system exemplifies this global approach, with telescopes in Chile, South Africa and Hawaii providing continuous monitoring of the entire visible sky. When the Chilean facility first detected Atlas on July 1st, the discovery triggered automated alerts that reached observatories worldwide within minutes. Ground-based networks now integrate seamlessly with space-based assets, creating observation campaigns that span from radio telescopes on Earth's surface to ultraviolet spectrographs beyond our atmosphere. The James Webb Space Telescope's observations of Atlas coordinate with simultaneous measurements from the Hubble Space Telescope, creating multi-wavelength datasets impossible to achieve with any single instrument. Amateur astronomers contribute significantly to these collaborative efforts, with citizen science networks like the Unistellar system providing distributed observations that complement professional facilities. Michael Yeager and Gerald Raymond's detection of the green transformation exemplifies how dedicated amateur observers often capture crucial developments that professional surveys might miss. The data-sharing protocols developed for Atlas observations will establish templates for studying future interstellar visitors. Standardized formats, rapid communication systems, and coordinated observing schedules maximize scientific return from objects that remain accessible for only brief periods. The computational challenge. Analyzing the flood of data generated by Atlas observations requires computational resources and algorithmic sophistication that pushes current technology to its limits. Each night of observations from major telescopes generates terabytes of raw data, requiring processing, calibration, and analysis before scientific interpretation becomes possible. Machine learning algorithms trained on vast databases of cometary observations attempt to identify patterns and anomalies in Atlas's behavior that human researchers might overlook. These systems analyze brightness variations, spectral changes, and morphological evolution across thousands of images with consistency and speed impossible for manual analysis. Advanced atmospheric modeling incorporates data from multiple spacecraft to understand how Atlas's outgassing interacts with the solar wind and interplanetary magnetic field. These simulations require supercomputer resources to model the complex physics of gas and dust dynamics in the harsh environment of interplanetary space. Orbital mechanics calculations trace Atlas's trajectory back through millions of years of galactic motion, accounting for gravitational perturbations from countless stellar encounters during its interstellar journey. These computations reveal probable origin regions while highlighting the fundamental uncertainties inherent in reconstructing ancient cosmic paths. The integration of observational data with theoretical models creates feedback loops that refine our understanding of cometary physics, galactic dynamics, and the properties of interstellar space. Each new measurement constrains theoretical possibilities while revealing additional complexities that require further investigation. The isotopic mysteries. High-resolution spectroscopy of Atlas may eventually reveal isotopic ratios that provide direct information about nuclear processes in its parent star system. Different stellar masses and evolutionary stages produce characteristic isotopic signatures that serve as fingerprints of their nuclear furnaces. The carbon-to-nitrogen ratio in Atlas's Comet already suggests formation conditions distinct from our solar system's environment. As spectroscopic precision improves, additional elemental ratios may reveal whether the comet formed around a star with different mass, age, or metallicity than our Sun. Isotopic analysis requires extremely high spectral resolution and signal-to-noise ratios that challenge current observational capabilities. The faintness of Atlas, combined with its rapid motion across the sky, limits exposure times and complicates the precise measurements needed for isotopic determination. Future space-based spectrographs with enhanced sensitivity and stability may enable detailed isotopic analysis of interstellar visitors, providing direct measurements of stellar nucleosynthesis processes throughout our galaxy. These data would test theories of galactic chemical evolution with unprecedented precision. The potential discovery of isotopic ratios impossible to produce in any known stellar environment would revolutionize our understanding of nuclear physics or suggest exotic formation scenarios beyond current theoretical frameworks. Such findings would rank among the most significant discoveries in modern astronomy. The thermal evolution. As Atlas approaches perihelion, thermal modeling attempts to predict how solar heating will affect its nucleus structure and composition. The unusual activity patterns observed so far suggest internal characteristics significantly different from typical solar system comets. Thermal penetration into the nucleus depends on factors including porosity, composition, thermal conductivity, and rotation rate, most of which remain poorly constrained for Atlas. The early onset of activity suggests either very low thermal inertia or composition dominated by highly volatile materials. Subsurface temperature profiles control the timing and intensity of outgassing as different chemical species reach sublimation temperatures at various depths within the nucleus. The steep activity increase observed in Atlas implies rapid thermal penetration or unusually shallow volatile reservoirs. Computer simulations model various nucleus compositions and structures, to match observed brightness and spectral evolution. These models suggest that Atlas may have a layered structure with different volatile distributions at various depths, possibly reflecting its formation history or modifications during interstellar travel. The dramatic color change from red to green indicates thermal activation of previously dormant chemical processes or structural changes that expose new material to solar radiation. Understanding these transformations requires detailed knowledge of how heat propagates through porous, heterogeneous materials under space conditions, the magnetic environment. Atlas travels through the complex magnetic environment of interplanetary space, where the solar wind carries embedded magnetic fields that interact with the charged particles in the comet's coma. These interactions create phenomena that may be detectable with appropriate instrumentation. Charged dust grains and ions in the coma respond to magnetic forces, potentially creating asymmetric structures or preferred outflow directions that depend on the local magnetic field orientation. Such effects might explain some of the unusual morphological features observed in Atlas's coma. The Parker Solar Probe, designed to study solar wind properties and magnetic field structure, may detect signatures of Atlas's interaction with the interplanetary environment during their close encounter near perihelion. These measurements could reveal how interstellar objects modify local space conditions. Magnetic field measurements from spacecraft throughout the solar system provide context for understanding how Atlas's passage affects the broader interplanetary environment. The comet's outgassing creates a small but detectable perturbation in the solar wind that propagates across millions of kilometers. Advanced plasma physics simulations model the complex interactions between the solar wind, interplanetary magnetic field, and Atlas's coma to predict observable signatures and understand the physical processes involved. These models require sophisticated numerical techniques and massive computational resources. The dust dynamics. The unusual polarization properties of Atlas suggest that its dust particles differ significantly from those found in solar system comets. These differences may reflect formation conditions, interstellar modifications, or compositional variations that affect particle structure and optical properties. Dust grain analysis using scattered light measurements attempts to determine particle size distributions, compositions, and morphologies that control how Atlas interacts with solar radiation. The deep negative polarization observed suggests particles with distinctive optical characteristics. Radiation pressure from the Sun accelerates dust particles away from Atlas's nucleus, creating the visible coma and potentially contributing to tail formation. The efficiency of this process depends on particle size, composition, and optical properties that remain poorly understood for interstellar material. Advanced scattering models incorporate various particle compositions and structures to match observed polarization and brightness measurements. These models suggest that Atlas may eject particles with complex morphologies or exotic compositions not found in typical cometary dust. The interaction between charged dust particles and the interplanetary magnetic field creates additional complexity in dust dynamics, potentially leading to asymmetric dust distributions or preferred ejection directions that contribute to the unusual morphological features observed in Hubble images. The spectroscopic evolution. The spectroscopic signature of Atlas continues evolving as changing solar heating activates different chemical processes within its nucleus. This evolution provides a real-time view of how interstellar material responds to stellar radiation. Early observations dominated by carbon dioxide emission are giving way to more complex spectra as additional molecular species reach sublimation temperatures. The dramatic increase in cyanide production represents just one example of how changing conditions activate new chemistry. High-resolution spectroscopy reveals Doppler shifts in emission lines that indicate expansion velocities and outflow patterns within the coma. These measurements constrain models of gas dynamics and help distinguish between different outgassing mechanisms. The sudden appearance of green emission suggests activation of chemistry involving carbon-bearing molecules, though the specific compounds responsible remain uncertain. Continued spectroscopic monitoring may identify the molecules causing this dramatic color change. Future observations will track how Atlas's spectrum evolves through perihelion passage and into the outbound phase. revealing how thermal cycling affects chemical processes in material formed around other stars. This temporal evolution provides unique insights into interstellar chemistry. The fragmentation risk. Intense solar heating during perihelion passage poses significant risks of nuclear fragmentation for Atlas, potentially destroying our opportunity to study an intact interstellar object. Many comets experience structural failure when thermal stresses exceed their mechanical strength. The unusual activity patterns and rapid brightening of Atlas may indicate internal structural modifications that affect its resistance to thermal stress. Early outgassing might have created internal fractures or weakened zones that become failure points under intense heating. Monitoring for signs of fragmentation requires high-resolution imaging that can detect small pieces separating from the main nucleus. Such observations demand excellent seeing conditions and sophisticated image processing to distinguish genuine fragments from temporary brightness variations. The Hubble Space Telescope's exceptional angular resolution makes it the premier instrument for detecting potential fragmentation events, though the comet's position near the Sun during perihelion limits observational opportunities when fragmentation risk is highest. Fragmentation would dramatically alter Atlas's subsequent evolution, potentially creating a debris stream that provides multiple targets for spectroscopic analysis, while simultaneously reducing the intensity of individual fragments below detection thresholds. The outgassing mechanisms, the specific physical processes driving Atlas's unusual outgassing patterns remain poorly understood, despite extensive observational and theoretical investigation. The early activation, rapid brightening, and unusual chemical composition suggest mechanisms different from typical cometary sublimation. Direct sublimation from the nucleus surface cannot account for the observed activity levels at large solar distances, suggesting either enhanced heat transfer within the nucleus or chemistry involving more volatile species than water ice. Carbon dioxide sublimation occurs at lower temperatures, but requires unusually high concentrations to explain the observations. Subsurface sublimation followed by gas transport through porous networks within the nucleus could explain some unusual features, though this mechanism requires specific structural characteristics that may not apply to interstellar objects with different formation histories. Explosive outgassing triggered by phase transitions, crystallization events, or chemical reactions could produce the rapid brightness variations observed in Atlas. Such processes might be activated by solar heating, but operate through mechanisms distinct from simple sublimation. The anomalous sunward extension of scattered light suggests directed outgassing or unusual particle dynamics that current models struggle to explain. Understanding this phenomenon requires new theoretical frameworks that may apply to interstellar objects but not solar system comets. The chemical inventory. The growing catalogue of chemical species detected in Atlas provides an increasingly detailed picture of its composition and the conditions present in its formation environment. Each new molecular identification adds constraints to models of stellar nuclear synthesis and planetary formation processes. Water, carbon dioxide, carbon monoxide, cyanide, and various organic compounds create a chemical inventory that differs significantly from typical solar system comets. The dominance of carbon dioxide over water particularly stands out as unusual for objects formed in our cosmic neighborhood. Trace species detection requires extremely sensitive spectroscopic techniques that push observational capabilities to their limits. Each additional molecular identification provides crucial information about formation conditions and evolutionary history. The absence of certain expected species may be as informative as positive detections, suggesting formation environments that lack typical cometary chemistry or evolutionary processes that have modified the original composition through chemical reactions or selective loss. Comparison with laboratory experiments on ice chemistry under various temperature and radiation conditions helps interpret the observed molecular inventory and constrain the physical conditions experienced by Atlas during its formation and interstellar journey. The nuclear structure. Understanding the internal structure of Atlas's nucleus presents fundamental challenges due to its small size and great distance from Earth. current observations provide only indirect constraints on density, porosity, composition, and structural characteristics. The relationship between nuclear size and observed activity suggests either very high volatile content or enhanced heat transfer efficiency compared to typical comets. These characteristics might reflect formation conditions or structural modifications during interstellar travel. Thermal modelling attempts to infer internal structure from observed outgassing patterns, though multiple structural scenarios can produce similar observational signatures. Distinguishing between different models requires additional constraints from future observations. Rotation period. Determination could provide information about nuclear shape and density distribution, though detecting brightness variations from such a distant object challenges current observational capabilities. Long-term photometric monitoring may eventually reveal rotational signatures. The unusual polarization properties suggest surface or near-surface characteristics that differ from typical cometary nuclei, possibly indicating compositional variations, structural modifications, or exotic materials not found in solar system objects. The formation environment. The chemical composition and physical characteristics of Atlas provide clues about the stellar environment where it formed billions of years ago. These ancient signatures preserve information about stellar nucleosynthesis and planetary system evolution in different galactic contexts. The unusually high carbon dioxide content suggests formation in a stellar system with different carbon to oxygen ratios than our solar system, possibly around stars with different masses, ages, or metallicities. Such variations affect the chemical inventory available for planetary formation. Isotopic ratios, when eventually determined, will provide direct information about nuclear processes in the parent star and constrain models of stellar evolution and galactic chemical evolution. These measurements represent our most direct access to stellar nuclear synthesis beyond our solar system. The apparent age of Atlas, potentially billions of years, means it formed when our galaxy had different chemical composition and stellar populations than today. Studying this ancient visitor provides insights into cosmic chemical evolution over galactic timescales. Comparing Atlas with other interstellar objects and solar system comets will reveal whether its unusual characteristics reflect typical conditions in other stellar systems or represent an exotic formation environment now rare or absent in our galactic neighborhood. The trajectory analysis. Detailed orbital calculations for Atlas attempt to trace its path back through millions of years of galactic motion to identify its possible origin star system. These computations require sophisticated models of galactic dynamics and stellar kinematics. The comet's current trajectory aligns closely with the galactic plane, suggesting formation in the thick disk population of older stars rather than the thin disk region where our Sun resides. This alignment provides important clues about its probable origin environment. Gravitational perturbations from stellar encounters during Atlas's interstellar journey have likely modified its original trajectory, making precise origin determination increasingly difficult for older objects. Statistical analysis can identify probable source regions even when specific parent stars remain unidentifiable. The high velocity of Atlas relative to our solar systems indicates either ejection from a high-velocity stellar system or acceleration through gravitational interactions during its interstellar journey. Understanding these dynamics requires detailed modeling of galactic structure and stellar motions. Future astrometric measurements will refine Atlas's orbital parameters and improve trajectory reconstructions, potentially identifying additional constraints on its origin region and evolutionary history. The observational legacy. The extensive observational campaign devoted to Atlas establishes new standards for studying transient astronomical phenomena and demonstrates the capabilities of modern coordinated astronomy. The techniques developed for this investigation will benefit future studies of similar objects. Archive data from multiple surveys extending back months before official discovery illustrate the value of maintaining comprehensive sky monitoring systems. These archives enable reconstruction of object evolution through periods when no targeted observations occurred. The integration of professional and amateur observations creates observational networks with geographic and temporal coverage impossible for any single institution. Citizen science contributions prove particularly valuable for monitoring rapidly evolving phenomena. Standardized data formats and rapid communication protocols developed for ATLAS observations will facilitate future coordinated campaigns, enabling more efficient use of limited observational windows for transient objects. The lessons learned from observing ATLAS inform the design of future survey systems and spacecraft missions, highlighting the observational capabilities needed to maximize scientific return from brief encounters with interstellar visitors. The theoretical frameworks. The unusual characteristics of ATLAS challenge existing theoretical frameworks for understanding cometary physics and force development of new models that can accommodate interstellar objects with properties outside the range observed in solar system comets. Traditional sublimation models based on water ice physics fail to explain the early activity and rapid brightening observed in ATLAS, requiring incorporation of more volatile species and complex thermal processes to match observations. The sunward extension of scattered light contradicts established understanding of radiation pressure and dust dynamics around comets, suggesting either exotic particle properties or novel physical processes not previously observed or theoretically predicted. Advanced computational models incorporating complex chemistry, multi-component physics, and three-dimensional structures attempt to reproduce the full range of observed phenomena. These models require substantial computational resources and sophisticated numerical techniques. The development of theoretical frameworks capable of explaining ATLAS's behavior advances our general understanding of cometary physics and prepares us for investigating future interstellar visitors that may display equally unusual characteristics. The detection statistics. The discovery rate of interstellar objects has increased dramatically with improved survey capabilities, suggesting that such visitors may be far more common than previously realized. Statistical analysis attempts to estimate the true population and frequency of these cosmic wanderers. 3 confirmed interstellar objects detected within 8 years implies a much larger population of fainter objects that escape detection with current technology. Advanced surveys coming online will dramatically increase our detection sensitivity and reveal the true abundance of interstellar visitors. Population models extrapolate from current detections to estimate the total number of interstellar objects passing through our solar system annually. These models suggest that several objects larger than 100 meters diameter may transit our cosmic neighborhood each year. The size distribution of detected interstellar objects shows strong observational bias toward larger, more active specimens. Future surveys with enhanced sensitivity will reveal whether small interstellar objects follow the same size distributions observed for solar system comets and asteroids. Long-term monitoring of interstellar object detection rates will constrain models of galactic stellar populations and planetary system evolution, providing insights into the efficiency of planetary formation processes throughout our cosmic neighborhood. The mission planning. The brief notice provided by current detection systems severely limits our ability to launch dedicated missions to study interstellar objects in detail. Future mission concepts must accommodate rapid response requirements or remain on standby for suitable targets. The European Space Agency's Comet Interceptor mission represents the first spacecraft designed specifically for studying pristine comets and potentially interstellar objects. This mission architecture enables investigation of targets identified with minimal advance warning. Advanced propulsion concepts under development could enable more ambitious interstellar object missions, including sample return capabilities that would bring material from other star systems directly to Earth-based laboratories for comprehensive analysis. Rapid response mission concepts require pre-positioned spacecraft, advanced propulsion systems, and streamlined mission planning processes that can be activated quickly when suitable targets appear. These capabilities demand new approaches to space mission design and implementation. The scientific return from dedicated interstellar object missions would far exceed that possible from remote observations alone, providing detailed compositional analysis, internal structure determination, and direct sampling of material from other stellar systems. The public interest. The discovery and unusual behavior of Atlas has captured public imagination in ways that typical astronomical discoveries rarely achieve. The combination of mystery, potential implications, and striking visual observations creates compelling narratives that resonate with diverse audiences. Social media coverage of Atlas demonstrates both the benefits and challenges of rapid information dissemination in the digital age. Accurate scientific information competes with sensationalized claims and speculative interpretations that can confuse public understanding. The second Comet narrative exemplifies how complex astronomical information can be misinterpreted and amplified through social media algorithms optimized for engagement rather than accuracy. Distinguishing between legitimate scientific discoveries and viral misinformation requires careful attention to sources and context. Educational opportunities presented by Atlas enable astronomy outreach that connects current research with fundamental questions about our place in the universe. The object's interstellar origin provides tangible connections to concepts that might otherwise remain abstract. Public interest in Atlas may influence funding priorities and mission planning for future interstellar object investigations, demonstrating the value of maintaining capabilities for studying these rare cosmic visitors. The technological advancement. The investigation of Atlas showcases how rapidly advancing technology enhances our capability to study faint, fast-moving objects throughout the solar system. Each new technological capability opens additional avenues for scientific investigation. Advanced detector technologies enable spectroscopic observations of objects too faint for previous generation instruments. These improvements particularly benefit studies of distant low-activity objects like Atlas during its approach phase. Machine learning algorithms trained on vast astronomical databases can identify subtle patterns and anomalies that human researchers might overlook. These tools prove particularly valuable for analyzing the complex, rapidly evolving datasets generated by Atlas observations. Improved computational capabilities enable sophisticated modeling of complex physical processes, allowing theoretical frameworks to keep pace with increasingly detailed observational constraints provided by modern instruments. The integration of ground-based and space-based observations creates synergistic capabilities that exceed the sum of individual contributions, enabling investigations impossible with any single observational platform. The future discoveries. The unusual characteristics revealed by Atlas suggest that future interstellar visitors may display equally surprising properties that challenge our current understanding of these cosmic wanderers. Each new detection adds to our growing appreciation of their diversity. Advanced survey systems coming online will detect interstellar objects at much greater distances, providing longer lead times for detailed study and potentially enabling spacecraft intercept missions with adequate advance warning. The accumulating database of interstellar object properties will enable statistical studies that reveal patterns and correlations invisible in small samples. These analyses may identify common characteristics or formation mechanisms that apply throughout our galaxy. Future space-based telescopes with enhanced sensitivity and spectroscopic capabilities will enable detailed chemical analysis of interstellar objects, potentially revealing isotopic signatures and exotic compounds that provide direct information about stellar nuclear synthesis processes. The development of rapid response spacecraft capabilities will transform our ability to study interstellar objects in detail, enabling investigations that provide comprehensive understanding rather than the limited snapshots possible with current remote observations. The galactic context. Atlas represents one sample from the vast population of small bodies ejected from planetary systems throughout our galaxy's history. Understanding its characteristics provides insights into planetary formation processes and stellar evolution across different galactic environments. The estimated age of Atlas, potentially billions of years, means it has witnessed galactic evolution over cosmologically significant timescales. Its composition preserves information about stellar nuclear synthesis and chemical conditions from earlier epochs in our galaxy's history. Comparing Atlas with other interstellar objects and solar system bodies reveals the diversity of formation environments and evolutionary processes that operate throughout our cosmic neighborhood. Each object represents a unique experiment in planetary formation. The trajectory of Atlas suggests origin in the thick disk stellar population, providing our first direct sample of material from this ancient galactic component. Future studies may reveal whether thick disk objects display systematically different compositions than thin disk counterparts. Statistical models of galactic structure and stellar evolution incorporate data from interstellar objects to constrain theories of galactic chemical evolution and planetary system formation efficiency across different stellar populations. The chemical clues. Each molecular species detected in Atlas provides constraints on the temperature, pressure, and chemical conditions present during its formation billions of years ago. The growing inventory of identified compounds creates an increasingly detailed picture of its origin environment. The unusual carbon dioxide dominance may reflect formation around stars with different carbon to oxygen ratios than our Sun, possibly indicating different stellar masses, evolutionary stages, or galactic chemical environments when the comet formed. Organic compound detection would provide crucial information about the prevalence of carbon chemistry in other stellar systems and potentially offer insights into the distribution of life's chemical precursors throughout our galaxy. Isotopic measurements, when eventually achieved, will provide direct constraints on nuclear processes in the parent star system and test models of stellar nuclear synthesis that currently rely entirely on astronomical observations and theoretical calculations. The temporal evolution of Atlas's chemical signature as it approaches and recedes from the Sun reveals how thermal processing affects interstellar material and provides insights into the physical structure and composition of its nucleus. The atmospheric interactions. As Atlas releases gas and dust into the surrounding space, complex interactions develop between its coma and the local electromagnetic environment. These processes create observable phenomena that provide additional diagnostic tools for understanding the comet's behavior and composition. The solar wind, carrying embedded magnetic fields and charged particles, encounters the neutral gases surrounding Atlas and initiates chemical reactions that produce ionized species detectable through characteristic emission lines. These interactions create a secondary chemistry distinct from the sublimation processes occurring at the nucleus surface. Ultraviolet radiation from the Sun photodissociates molecular species in the coma, breaking apart complex compounds and creating fragments that may not exist under terrestrial conditions. This photochemistry produces short-lived species that challenge detection but provide crucial information about the parent molecules from which they derive. The Parker Solar Probe's upcoming observations of Atlas will occur within the solar wind environment, where these interactions reach maximum intensity. The spacecraft's plasma instruments may detect perturbations in the solar wind caused by the comet's passage, revealing information about outgassing rates and coma composition invisible to remote observations. Magnetohydrodynamic simulations model the complex interactions between the solar wind, interplanetary magnetic field, and Atlas's expanding coma to predict observable signatures and understand the underlying physics. These calculations require sophisticated numerical methods and massive computational resources to capture the relevant physical processes. The dust properties investigation. The unusual polarization characteristics of Atlas suggest that its dust particles possess properties significantly different from those found in solar system comets. Understanding these differences provides insights into formation conditions and evolutionary processes in other stellar systems. Light scattering measurements attempt to determine particle size distributions, refractive indices, and morphologies that control how Atlas interacts with solar radiation. The deep negative polarization observed indicates particles with distinctive optical characteristics that may reflect exotic compositions or unusual structures. Laboratory experiments on analog materials help interpret the polarization measurements by providing controlled studies of how different particle compositions and structures affect light scattering properties. These experiments reveal that the observed polarization signature requires either unusual compositions or particle morphologies not typical of terrestrial materials. Advanced electromagnetic scattering calculations model various particle compositions, sizes, and shapes to match observed polarization and brightness measurements. These models suggest that Atlas may eject particles with complex internal structures or surface properties that reflect formation in different chemical environments. The temporal evolution of polarization properties as Atlas approaches perihelion may reveal changes in particle characteristics caused by thermal processing or the activation of different outgassing sources within the nucleus. Such evolution would provide unique insights into how solar heating affects interstellar material. The fragmentation dynamics. The intense thermal stresses experienced during perihelion passage pose significant risks for nuclear fragmentation that could fundamentally alter Atlas's subsequent evolution. Historical observations of comet breakup events provide context for assessing this possibility. Thermal expansion and contraction cycles can create internal fractures that weaken the nuclear structure, making it more susceptible to disruption from gas pressure or rotational stresses. The porous heterogeneous structure typical of cometary nuclei makes them particularly vulnerable to thermal stress fracturing. Sublimation pressure from trapped gases within the nucleus can exceed the mechanical strength of the surrounding material, leading to explosive outgassing events that fragment portions of the nucleus. Such events often produce dramatic brightness increases followed by the appearance of multiple components in high-resolution images. Monitoring at LAS for signs of fragmentation requires high angular resolution imaging capable of detecting small pieces separating from the main nucleus. The Hubble Space Telescope provides the best available capability for such observations, though the comet's position relative to the Sun limits observational opportunities during the highest risk period. Mathematical models of nuclear structure and thermal evolution attempt to predict fragmentation probability based on estimated composition, porosity, and mechanical properties. These models incorporate laboratory measurements of ice mechanical properties and thermal expansion coefficients under space conditions. The comparative analysis. Detailed comparison between Atlas and the two previously observed interstellar objects reveals both similarities and crucial differences that illuminate the diversity of these cosmic visitors. Each object represents a unique sample from different stellar environments and evolutionary histories. Oumuamua displayed no detectable outgassing despite showing non-gravitational acceleration, suggesting either very low volatile content or unusual physical properties that prevented gas detection. Its elongated shape and rapid rotation created challenges for theoretical interpretation that remain unresolved. Borisov appeared more similar to typical solar system comets, with clearly detectable water vapor and dust emission that followed expected patterns for increasing solar heating. However, its chemical composition showed subtle differences that indicated formation in a different stellar environment. Atlas combines characteristics from both previous visitors while displaying unique features not observed in either predecessor. The early activity, unusual chemical composition, rapid brightening, and anomalous morphology create a distinctive profile that expands our understanding of interstellar object diversity. Statistical analysis of the small sample of known interstellar objects suggests that each represents a different class or formation environment, implying enormous diversity in the population of objects wandering between stars. Future detections will test whether this apparent diversity reflects true population characteristics or observational selection effects. The accumulating data from multiple interstellar objects enable comparative studies that may reveal common formation mechanisms or evolutionary processes while highlighting the unique characteristics that distinguish objects from different stellar systems. The nucleus modeling. Understanding the internal structure and composition of Atlas requires sophisticated theoretical models that incorporate observational constraints while accounting for the fundamental uncertainties inherent in studying such distant, small objects. Thermal models attempt to reproduce observed outgassing patterns by varying nucleus composition, porosity, thermal conductivity, and structural characteristics. These models reveal that multiple parameter combinations can produce similar observational signatures, highlighting the challenges of uniquely determining internal properties. The early onset of activity suggests either very high volatile content or enhanced heat transfer mechanisms that allow solar heating to penetrate deeply into the nucleus, even at large distances from the Sun. Such characteristics might reflect formation conditions or structural modifications during interstellar travel. Layered models incorporating different volatile distributions at various depths within the nucleus attempt to explain the complex temporal evolution of Atlas's activity. These models suggest that thermal penetration progressively activates different chemical reservoirs as the comet approaches perihelion. Advanced computational techniques enable three-dimensional modeling of nucleus structure with realistic heterogeneity, porosity variations, and complex chemical distributions. These simulations require substantial computational resources, but provide detailed predictions for comparison with observations. The velocity analysis. The extreme velocity of Atlas relative to our solar system provides crucial information about its origin and evolutionary history. Objects ejected from nearby stellar systems should display velocities related to the kinematics of their parent stars and the efficiency of ejection mechanisms. Stellar encounter modeling attempts to reproduce Atlas's observed velocity through gravitational interactions with massive objects during its interstellar journey. These calculations reveal that multiple stellar encounters could modify the original ejection velocity and complicate efforts to identify the parent system. The alignment of Atlas's trajectory with the galactic plane suggests possible origin in the thick disk stellar population, which displays different kinematic characteristics than the thin disk region where our Sun resides. This alignment provides statistical constraints on probable origin regions. Galactic orbit calculations trace Atlas's motion through the galaxy's gravitational field over millions of years, accounting for the complex dynamics of stellar systems embedded within the galactic potential. These computations reveal probable paths and highlight regions where the comet may have originated. The high velocity also indicates that Atlas will escape our solar system with substantial kinetic energy, carrying it into interstellar space where it may eventually encounter other stellar systems and potentially influence their chemical evolution through cross-contamination. The observational challenges. Studying Atlas presents numerous technical challenges that push current observational capabilities to their limits. The combination of faintness, rapid motion, and limited observational windows demands innovative approaches and careful coordination between multiple facilities. Tracking rapidly moving objects requires sophisticated telescope control systems that can accurately follow predicted trajectories while maintaining precise pointing for long-exposure spectroscopy. Small errors in orbital prediction can result in the target moving outside the telescope field of view during extended observations. Atmospheric turbulence particularly affects observations of faint, distant objects like Atlas, requiring excellent seeing conditions or adaptive optics systems to achieve the resolution needed for detailed morphological studies. Many planned observations depend on favourable weather conditions that cannot be guaranteed. The comet's position relative to the Sun creates additional complications, with solar conjunction rendering ground-based observations impossible during the most scientifically interesting period around perihelion. Space-based observatories become crucial for maintaining observational coverage during this critical phase. Coordinating observations between multiple facilities across different time zones requires careful scheduling and communication to ensure that data collection proceeds efficiently despite equipment failures, weather delays, or other unforeseen complications that commonly affect astronomical observations. The spectroscopic techniques. Advanced spectroscopic analysis of Atlas requires sophisticated techniques that can extract weak signals from complex backgrounds while accounting for the comet's rapid motion and varying observational conditions. High-resolution spectroscopy attempts to resolve individual emission lines from different molecular species, enabling precise velocity measurements and abundance determinations that constrain models of chemochemistry and dynamics. Such observations require large telescopes and extended exposure times. Multi-wavelength spectroscopy spanning ultraviolet, visible, and infrared regions provides comprehensive coverage of different molecular transitions and electronic states. Each wavelength range offers unique diagnostic capabilities for identifying specific chemical species and physical conditions. Doppler shift measurements of emission lines reveal gas expansion velocities and outflow patterns within the coma, providing information about the physical processes driving outgassing and the structural characteristics of the nucleus. These measurements require extremely precise wavelength calibration. Time-resolved spectroscopy tracks rapid changes in emission line intensities and ratios that may indicate variable outgassing, chemical reactions, or structural modifications within the nucleus. Such observations demand continuous monitoring over extended periods with consistent instrumental setup. Polarization spectroscopy examines how the polarization state of emission lines varies with observational geometry and molecular characteristics, providing additional constraints on physical conditions and chemical processes that complement intensity measurements. The chemical evolution. The changing chemical signature of Atlas as it approaches perihelion provides real-time observations of how thermal processing affects interstellar material and activates previously dormant chemical reservoirs within the nucleus. Early observations dominated by carbon dioxide emission are progressively supplemented by additional molecular species as increasing solar heating reaches deeper into the nucleus and activates more volatile components. This evolution reveals the chemical stratification within the nucleus. The dramatic increase in cyanide production represents just one example of how changing thermal conditions activate new chemistry. The steep power law dependence on solar distance suggests either unusual chemical kinetics or structural characteristics that amplify thermal effects. Organic molecule detection becomes increasingly likely as thermal processing breaks down complex compounds and releases simpler fragments detectable through characteristic emission signatures. Such detections would provide crucial information about carbon chemistry and other stellar systems. The temporal sequence of chemical activation may reveal information about nucleus structure and formation history, with different chemical reservoirs becoming accessible as thermal penetration reaches various depths within the heterogeneous nucleus. Understanding how Atlas's chemistry evolves through perihelion passage and into the outbound phase will provide insights into how thermal cycling affects materials formed in other stellar systems and may reveal chemical processes unique to interstellar objects. The particle acceleration. The unusual sunward extension of scattered light around Atlas suggests particle acceleration or transport mechanisms that differ from typical cometary processes. Understanding these mechanisms requires careful analysis of particle dynamics in the complex electromagnetic environment surrounding the comet. Radiation pressure from solar photons normally accelerates dust particles away from the Sun, creating the familiar anti-solar tail structure observed in most comets. The apparent reversal of this effect in Atlas challenges our understanding of particle physics in cometary environments. Electromagnetic effects involving charged dust grains and the interplanetary magnetic field could potentially create unusual particle trajectories that contribute to the observed sunward extension. Such effects depend on particle size, charge state, and local magnetic field conditions. Gas drag forces from expanding neutral gases in the coma can influence particle motion, particularly for small grains that couple efficiently to gas flows. Complex gas dynamics driven by non-uniform outgassing could create particle transport patterns that differ from simple radiation pressure acceleration. Electrostatic charging of dust particles in the solar wind environment creates additional forces that may contribute to unusual particle trajectories. The balance between gravitational, electromagnetic, and radiation pressure forces determines particle motion and observable signatures. Advanced particle dynamics simulations incorporating realistic electromagnetic environments and complex outgassing patterns attempt to reproduce the observed morphological features and understand the underlying physical processes responsible for the unusual sunward extension. The thermal penetration. Solar heating of Atlas creates temperature gradients within the nucleus that drive sublimation and outgassing at various depths below the surface. Understanding these thermal processes requires detailed modelling of heat transfer through porous, heterogeneous materials under space conditions. Thermal diffusion calculations predict how solar heating penetrates into the nucleus as a function of thermal conductivity, porosity, and composition. These models reveal that typical cometary materials require substantial solar heating before interior temperatures reach sublimation thresholds just for common ices. The early activity observed in Atlas suggests either unusually efficient heat transfer or composition dominated by species that sublimate at lower temperatures than water ice. Carbon dioxide and carbon monoxide both sublimate at temperatures well below water, potentially explaining the early onset of activity. Thermal modelling must account for the complex feedback between sublimation and heat transfer, as gas production removes latent heat while creating pathways for enhanced thermal conduction. These coupled processes create nonlinear behaviour that complicates theoretical predictions. Subsurface temperature monitoring through thermal emission measurements provides observational constraints on thermal models and helps distinguish between different scenarios for nucleus structure and composition. Such observations require sensitive infrared instruments and careful subtraction of reflected sunlight. The thermal evolution of Atlas through perihelion passage will test theoretical models and may reveal thermal behavior unique to interstellar objects with different formation histories and structural characteristics than solar system comets. The rotation determination. Measuring the rotation period of Atlas presents significant observational challenges due to its small size, great distance, and low amplitude brightness variations. However, successful rotation determination would provide crucial information about nucleus shape, density distribution, and structural integrity. Photometric monitoring attempts to detect periodic brightness variations caused by rotation of an irregularly shaped nucleus or heterogeneous surface composition. Such variations typically produce amplitude changes of only a few %, requiring precise measurements over extended periods. The rotation period affects how solar heating is distributed across the nucleus surface, influencing outgassing patterns and potentially creating observable asymmetries in the coma or tail structure. Understanding rotational effects helps interpret morphological observations. Rapid rotation can create centrifugal stresses that exceed the mechanical strength of loosely bound cometary material, potentially leading to mass shedding or structural failure. Conversely, slow rotation may indicate either high density or significant internal cohesion. Non-principal axis rotation, common among small solar system bodies, creates complex photometric signatures that require sophisticated analysis techniques to extract meaningful physical parameters. Such rotation states may result from previous fragmentation events or asymmetric outgassing torques. Successful rotation determination for Atlas would provide the first such measurement for an interstellar object and enable comparison with rotation properties of solar system comets to test whether formation in different stellar environments produces objects with distinctive rotational characteristics. The contamination assessment. The passage of Atlas through our solar system raises questions about contamination exchange between interstellar objects and our local environment. Understanding these processes has implications for astrobiology and the chemical evolution of planetary systems. Solar wind particles carrying isotopic signatures characteristic of our Sun may be incorporated into Atlas's surface or coma, creating contamination that could complicate future chemical analysis. The efficiency of such processes depends on interaction cross-sections and residence times. Interplanetary dust grains from solar system sources may collide with Atlas during its passage, embedding foreign material that alters surface composition and potentially affects subsequent outgassing behavior. Such contamination could produce misleading chemical signatures. Conversely, Atlas sheds material into interplanetary space that may eventually be incorporated into solar system bodies or collected by future sample return missions. This material carries chemical signatures from other stellar systems and represents a form of natural cross-contamination between star systems. Atmospheric escape from Earth and other planets contributes trace amounts of planetary material to interplanetary space, some of which may be collected by passing interstellar objects. While extremely dilute, such contamination provides a mechanism for transferring planetary signatures across interstellar distances. Understanding contamination processes helps assess the pristine nature of interstellar objects and guides interpretation of chemical analyses that may detect unexpected signatures resulting from contamination rather than intrinsic composition. the mission architecture. Future dedicated missions to study interstellar objects require innovative spacecraft designs and mission architectures that can accommodate the rapid response timelines and extreme velocity requirements imposed by these brief visitors to our solar system. Rapid launch capabilities demand pre-positioned spacecraft or advanced propulsion systems that can achieve the velocity changes needed to intercept fast-moving interstellar objects. Conventional chemical propulsion proves inadequate for most intercept scenarios without unrealistic propellant requirements. Solar sail technology offers potential advantages for interstellar object missions, providing continuous acceleration without propellant consumption and enabling trajectory modifications after launch. However, solar sails require large surface areas and sophisticated attitude control systems. Nuclear propulsion concepts under development could provide the high specific impulse needed for ambitious interstellar object missions, including potential sample return capabilities that would revolutionize our understanding of these cosmic visitors. Such systems require substantial technological development and testing. Mission designs must accommodate the limited warning time available when interstellar objects are detected, requiring pre-approved mission concepts, standby spacecraft, and streamlined decision-making processes that can be activated quickly when suitable targets appear. The scientific return from dedicated interstellar object missions would far exceed that possible from remote observations alone, providing detailed compositional analysis, internal structure determination, and potentially returning samples from other stellar systems to Earth-based laboratories. The database. Development. Each interstellar object detection contributes valuable data to a growing database that will eventually enable statistical studies of these cosmic wanderers and their relationship to galactic structure and stellar evolution processes. Standardized data formats and analysis procedures ensure that observations from different facilities and time periods can be combined effectively for comparative studies and population analysis. Such standards require coordination between international astronomical organizations. The accumulating database will eventually reveal correlations between object characteristics and trajectory properties that may indicate common formation mechanisms or evolutionary processes operating throughout our galactic neighborhood. Machine learning algorithms trained on large datasets may identify subtle patterns and relationships that escape traditional statistical analysis, potentially revealing new categories of interstellar objects or unexpected correlations between observable properties. Long-term database maintenance requires careful curation and quality control to ensure that data remain accessible and useful for future researchers using analysis techniques not yet developed. Archival standards must anticipate technological evolution and changing research needs. The database will serve as a crucial resource for planning future observations and missions, enabling researchers to identify knowledge gaps and prioritize investigations that will maximize scientific return from limited observational opportunities. The theoretical advances. The unusual characteristics of Atlas are driving advances in theoretical understanding of cometary physics, dust dynamics, and thermal processes that will benefit studies of both interstellar and solar system objects. Advanced computational models incorporating complex chemistry, multi-phase physics, and three-dimensional structures are being developed to explain the full range of observed phenomena. These models require sophisticated numerical techniques and substantial computational resources. New theoretical frameworks for understanding particle acceleration and transport in cometary environments are emerging to explain the unusual morphological features observed in Atlas. These frameworks may apply to other astronomical contexts involving dust and gas interactions. Improved models of thermal processes in heterogeneous, porous materials are being developed to understand how solar heating affects objects with different formation histories and structural characteristics than typical solar system bodies. The integration of observational constraints with theoretical predictions creates feedback loops that refine our understanding of fundamental physical processes while revealing areas where current models remain incomplete or inaccurate. These theoretical advances will improve our ability to interpret observations of future interstellar objects and may reveal universal principles that apply to small body physics throughout the galaxy. The detection evolution. The discovery of Atlas demonstrates how modern survey capabilities have revolutionized our ability to detect and study interstellar objects, while pointing toward even more dramatic improvements expected from next-generation facilities. Current surveys achieve detection rates limited by telescope aperture, detector sensitivity, and data processing capabilities. Upcoming facilities will improve all these factors, dramatically increasing the discovery rate for interstellar objects. The Vera Rubin Observatory, scheduled to begin operations soon, will survey the entire visible sky every few nights with unprecedented sensitivity, potentially detecting dozens of interstellar objects annually once fully operational. Advanced data processing algorithms incorporating machine learning and artificial intelligence will enable real-time identification of moving objects and rapid classification of their orbital characteristics, accelerating the time between detection and follow-up observations. Space-based survey systems under development will provide continuous monitoring capabilities unaffected by weather, atmospheric turbulence, or daylight constraints that limit ground-based observations. Such systems could detect interstellar objects at much greater distances. The evolution from detecting a few interstellar objects per decade to potentially dozens per year will transform our understanding of these cosmic visitors from studies of individual oddities to statistical analyses of representative populations. The international cooperation. The study of Atlas exemplifies how modern astronomy requires international cooperation to maximize scientific return from brief observational opportunities. Coordinated efforts spanning multiple continents and organizations prove essential for comprehensive investigation. Time zone differences enable continuous monitoring as objects move across the sky, with observations being handed off between facilities as Earth's rotation brings different telescopes into favorable positions. Such coordination requires careful planning and reliable communication systems. Resource sharing allows access to specialized instruments and techniques that no single institution could maintain independently. International partnerships enable investigations that would be impossible for any individual organization to undertake. Standardized protocols for data sharing and analysis facilitate rapid collaboration between research groups worldwide, enabling comprehensive studies that incorporate diverse observational perspectives and analytical techniques. The success of international cooperation in studying Atlas establishes templates for investigating future interstellar objects and demonstrates the benefits of coordinated astronomical research for addressing complex scientific questions. Future interstellar object investigations will benefit from the collaborative frameworks established during Atlas observations, enabling more efficient use of global astronomical resources and maximizing scientific return from these rare cosmic encounters. The educational impact. The discovery and investigation of Atlas provides exceptional opportunities for public education and outreach that connect current research with fundamental questions about our place in the universe and the nature of cosmic evolution. The interstellar origin of Atlas captures public imagination in ways that typical astronomical discoveries rarely achieve, providing natural entry points for discussing stellar evolution, galactic structure, and the processes that shape our cosmic environment. Real-time observations enable educational programs that follow scientific investigations as they unfold, demonstrating how astronomical research actually proceeds and highlighting both the excitement and challenges of frontier science. The interdisciplinary nature of Atlas studies showcases how modern astronomy integrates physics, chemistry, geology, and computer science to address complex scientific questions that require diverse expertise and analytical approaches. Educational materials developed for Atlas outreach will serve as resources for future interstellar object discoveries, building public understanding of these cosmic visitors and their scientific significance for understanding galactic evolution. The global nature of Atlas observations demonstrates how international scientific cooperation addresses questions that transcend national boundaries and require collaborative approaches that reflect the universal nature of scientific inquiry. The future implications. The investigation of Atlas represents just the beginning of a new era in interstellar object studies that will dramatically expand our understanding of galactic structure, stellar evolution, and the diversity of planetary formation processes throughout our cosmic neighborhood. Improved detection capabilities will reveal whether Atlas represents a typical example of interstellar visitors or an unusual specimen that happens to have captured our attention. The true diversity of these objects remains largely unknown. Dedicated missions to study interstellar objects in detail will provide comprehensive understanding that complements but far exceeds the information available from remote observations alone. Such missions may reveal entirely unexpected characteristics invisible to Earth-based studies. The accumulating database of interstellar object properties will enable statistical studies that reveal patterns and correlations invisible in small samples, potentially identifying formation mechanisms and evolutionary processes that operate throughout our galaxy. Long-term monitoring of interstellar object detection rates and characteristics will provide insights into galactic evolution, stellar system formation efficiency, and the processes that regulate material exchange between different regions of our cosmic neighborhood. The techniques developed for studying Atlas will benefit investigations of solar system objects, enabling more detailed characterization of comets, asteroids, and other small bodies that preserve information about our own planetary system's formation and evolution. The quantum mechanical processes. At the molecular level, Atlas exhibits quantum mechanical processes that govern how absorbed solar energy drives chemical reactions and phase transitions within its nucleus. Understanding these fundamental mechanisms requires sophisticated theoretical frameworks that bridge quantum chemistry and macroscopic thermodynamics. Photodissociation of molecular species in the coma occurs when ultraviolet photons possess sufficient energy to break chemical bonds, creating reactive fragments that may recombine into new compounds or escape into space. These quantum processes determine which molecules survive long enough for spectroscopic detection. Electronic excitation states in various molecular species produce the characteristic emission lines observed in Atlas's spectrum. Each transition corresponds to specific quantum energy levels that depend on molecular structure and environmental conditions within the coma. Vibrational and rotational quantum states of molecules provide additional spectroscopic signatures that reveal temperature, density, and chemical composition within different regions of the expanding coma. These quantum signatures enable remote determination of physical conditions impossible to measure directly. Quantum tunneling effects in chemical reactions become significant at the low temperatures characteristic of cometary nuclei, potentially enabling chemical processes that would be forbidden under classical thermodynamics. Such effects may contribute to the unusual chemistry observed in Atlas. The quantum mechanical nature of photon interactions with matter determines absorption and emission efficiencies that control how solar radiation heats the nucleus and drives out gassing processes. Understanding these interactions requires detailed quantum calculations for complex molecular systems. The hydrodynamic modeling, the expansion of gas and dust from Atlas's nucleus, creates complex hydrodynamic flows that determine coma structure, particle transport, and observable morphological features. These processes require sophisticated fluid dynamics, modeling that accounts for multi-component flows and varying thermodynamic conditions. Gas expansion from discrete source regions on the nucleus surface creates jets and collimated outflows that interact with the ambient coma environment through shock formation, turbulent mixing, and momentum transfer processes. These interactions shape the overall coma structure and particle distributions. Dust grain entrainment in expanding gas flows depends on particle size, gas density, and local velocity gradients that vary throughout the coma. Small particles couple efficiently to gas motion, while larger grains follow more independent trajectories determined by gravitational and radiation pressure forces. Non-equilibrium. Thermodynamics characterize conditions within the expanding coma, where different molecular species may have distinct temperatures and velocity distributions that evolve as the gas expands and cools. These conditions affect chemical reaction rates and spectroscopic signatures. Computational fluid dynamics simulations incorporate realistic nucleus geometry, heterogeneous outgassing sources, and multi-species chemistry to predict observable coma characteristics. These calculations require substantial computational resources and sophisticated numerical methods to capture relevant physical processes. The unusual morphological features observed in Atlas, particularly the sunward extension of scattered light, challenge existing hydrodynamic models and may require new theoretical frameworks that incorporate exotic physics or unusual boundary conditions, the magnetic field interactions. Atlas's passage through the heliosphere exposes it to complex magnetic field environments that influence charged particle motion, plasma chemistry, and electromagnetic signatures detectable by sensitive instruments. These interactions provide additional diagnostic tools for understanding the comet's behavior. The interplanetary magnetic field embedded in the solar wind creates preferred directions for charged particle motion that may contribute to asymmetric coma structures or directional outflow patterns. Such effects depend on the local magnetic field orientation and strength at the comet's position. Photoionization of neutral species in the coma creates charged particles that respond to electromagnetic forces differently than their neutral counterparts. These ions follow complex trajectories determined by the balance between gravitational, electric, and magnetic forces. Magnetic reconnection events in the solar wind environment may create localized acceleration regions that affect charged particles near Atlas, potentially contributing to unusual particle signatures or electromagnetic emissions detectable by radio telescopes. Plasma instabilities driven by the interaction between the solar wind and Atlas's ionosphere may generate electromagnetic waves detectable at radio frequencies. Such emissions would provide information about plasma conditions and magnetic field structures near the comet. Advanced magnetohydrodynamic simulations model the complex interactions between Atlas's expanding coma and the magnetized solar wind environment to predict observable electromagnetic signatures and understand the underlying physics of these interactions. The isotopic signatures. Future high-resolution spectroscopic observations may eventually determine isotopic ratios in Atlas that provide direct information about nuclear processes in its parent star system and constrain models of stellar nucleosynthesis and galactic chemical evolution. Carbon isotope ratios reflect the balance between different nuclear burning processes in the parent star, with carbon-12 to carbon-13 ratios serving as indicators of stellar mass, evolutionary stage, and metallicity. These measurements require extremely high spectral resolution and signal-to-noise ratios. Oxygen isotope signatures provide information about stellar nucleosynthesis pathways and potential contamination from supernova in the stellar environment where Atlas formed. Different isotopic ratios indicate formation around stars with varying masses and evolutionary histories. Nitrogen isotope measurements constrain models of stellar evolution and galactic chemical evolution by revealing the efficiency of nitrogen production in different stellar environments. These signatures preserve information about conditions billions of years ago when Atlas formed. Deuterium to hydrogen ratios provide insights into primordial nuclear synthesis and subsequent chemical processing in interstellar space and stellar environments. Such measurements challenge current observational capabilities but would provide unique constraints on cosmological and galactic evolution models. The technical challenges of isotopic measurements from such distant, faint objects require next-generation instruments with unprecedented sensitivity and spectral resolution. Future space-based observatories may eventually achieve the capabilities needed for detailed isotopic analysis. The chemical network modeling. The complex chemistry occurring within Atlas's coma involves hundreds of potential reactions between various molecular species, ions and radicals created by solar radiation and electron impact processes. Understanding this chemistry requires sophisticated network models that track all relevant species and reactions. Gas phase chemistry in the coma environment operates under conditions far from thermodynamic equilibrium, with reaction rates controlled by radiation fields, temperature gradients, and density variations that change continuously as the coma expands and evolves. Photochemical models incorporate detailed cross-sections for photodissociation, photoionization, and electronic excitation processes that determine how solar ultraviolet radiation drives chemical reactions and creates observable emission signatures. Electron impact chemistry becomes important in regions where photoionization creates significant electron populations that can drive additional chemical reactions through collisional processes. These reactions may produce species not formed through photochemical pathways alone. Surface chemistry on dust grains provides additional reaction pathways that may be particularly important for forming complex organic molecules through heterogeneous catalysis. Such processes could create chemical signatures that differ from pure gas phase chemistry. Chemical network calculations predict the abundances of hundreds of molecular species and their evolution with time and position within the coma. These models enable interpretation of spectroscopic observations and guide the search for new molecular signatures. The formation scenarios. The unusual characteristics of Atlas constrained theoretical models of its formation environment and evolutionary history, providing insights into planetary system formation processes around different types of stars throughout galactic history. Formation around a metal-poor star in the galactic thick disk could explain the unusual chemical composition, with different stellar nucleosynthesis products creating distinctive ice compositions not found in our solar system's formation environment. Alternative formation scenarios involve capture of interstellar material during passage through dense molecular clouds, potentially explaining unusual isotopic signatures or chemical compositions that reflect interstellar rather than stellar system processing. Collision fragmentation of larger bodies within the parent planetary system could produce objects with unusual structural characteristics or chemical distributions that influence subsequent outgassing behavior and observational signatures. Late-stage thermal processing in the parent system might have modified the original composition through sublimation and reaccretion processes that created the layered structure suggested by Atlas's complex activity patterns. Tidal disruption during ejection from the parent system could have created internal fractures or structural modifications that affect thermal conduction and outgassing efficiency in ways that distinguish interstellar objects from solar system comets. Each formation scenario predicts different observable characteristics that can be tested through continued observations and theoretical modeling, potentially enabling determination of Atlas's true origin and evolutionary history. The galactic archaeology. Atlas represents a direct sample of material from distant regions of our galaxy, potentially preserving chemical signatures from stellar environments that no longer exist or have evolved significantly since the comet's formation billions of years ago. The thick disk origin suggested by Atlas's trajectory indicates formation around ancient stars that existed when our galaxy had different chemical composition and structure than today. Such objects provide unique windows into galactic evolution over cosmic timescales. Chemical signatures preserved in Atlas may reveal information about stellar nucleosynthesis processes in early galactic history, when metallicity was lower and stellar populations differed significantly from those present in our current galactic neighborhood. Comparison between multiple interstellar objects from different galactic regions and evolutionary epochs will eventually enable mapping of chemical evolution throughout our galaxy's history, providing observational tests of theoretical models of galactic formation and evolution. The preservation of ancient chemical signatures depends on the thermal and radiation environment experienced during Atlas's interstellar journey, with cosmic ray bombardment and occasional stellar encounters potentially modifying surface composition over millions of years. Future studies of Atlas and similar objects will contribute to the emerging field of galactic archaeology, using small bodies as fossils that preserve information about cosmic chemical evolution over billions of years. The astrobiology implications. While Atlas shows no obvious signs of biological activity, its study provides insights into the distribution of organic chemistry throughout our galaxy and the potential for life-bearing materials to travel between stellar systems. The detection of organic compounds in Atlas would demonstrate that carbon chemistry capable of supporting biological processes occurs in other stellar systems, potentially indicating widespread distribution of life's chemical precursors throughout our galaxy. Interstellar panspermia scenarios suggest that life-bearing materials could travel between star systems via objects like Atlas, though the extreme conditions of interstellar space make survival of complex biological systems highly unlikely over million-year timescales. The chemical diversity observed in Atlas and other interstellar objects indicates that planetary systems throughout our galaxy may have access to chemical inventories significantly different from those available during Earth's formation, potentially leading to exotic biochemistries. Contamination studies reveal how materials exchange between stellar systems through interstellar visitors, creating natural experiments in chemical transport that may influence the development of life in recipient planetary systems. Future interstellar object missions with enhanced biological detection capabilities may search for organic signatures, or even preserved biological materials that could revolutionize our understanding of life's distribution throughout the cosmos. The observational legacy. The extensive observational campaign devoted to Atlas has established new paradigms for studying transient astronomical phenomena and created datasets that will support research for decades to come. Archive development ensures that Atlas observations remain accessible to future researchers using analysis techniques not yet developed, maximizing the long-term scientific return from this unique opportunity to study an interstellar visitor. Methodological advances developed for Atlas observations will benefit studies of future interstellar objects, solar system comets, and other astronomical phenomena that require rapid response capabilities and coordinated multi-facility campaigns. The integration of professional and amateur observations demonstrates the value of citizen science networks for monitoring rapidly evolving phenomena and highlights the importance of maintaining diverse observational capabilities. Data analysis techniques pioneered for Atlas will find applications in other areas of astronomy where similar challenges arise in studying faint, rapidly moving objects with complex temporal evolution. The collaborative frameworks established during Atlas observations provide templates for future international astronomical projects that require coordination between diverse institutions and rapid sharing of time-critical information. The technological innovations. Studying Atlas has driven innovations in observational techniques, data analysis methods, and theoretical modeling approaches that advance the broader capabilities of astronomical research. Advanced image processing algorithms developed to extract weak signals from Atlas observations will benefit studies of other faint astronomical objects where traditional techniques prove inadequate. Machine learning applications for automated detection and classification of moving objects have been refined through Atlas observations, improving our ability to identify and characterize future interstellar visitors. Spectroscopic techniques optimized for rapid cadence observations of faint objects enable new approaches to studying variable astronomical phenomena across diverse fields of astronomy. Computational modeling advances driven by the need to understand Atlas's unusual characteristics will improve theoretical frameworks for studying cometary physics, dust dynamics, and thermal processes in small bodies. The integration of ground-based and space-based observations has been optimized through Atlas studies, creating more efficient approaches to coordinated astronomical campaigns. Atlas has captured public imagination in unprecedented ways, creating opportunities for science communication and education that connect current research with fundamental questions about our cosmic environment. Social media engagement demonstrates both the potential and challenges of communicating complex scientific discoveries to diverse audiences, highlighting the need for accurate information sources and clear explanations of uncertainties and limitations. Educational programs developed around Atlas observations provide real-time examples of how scientific research proceeds, showcasing both the excitement of discovery and the careful methodology required for reliable results. The international nature of Atlas studies illustrates how modern astronomy transcends political boundaries and represents humanity's collective effort to understand our place in the universe. Public interest in Atlas may influence funding priorities and mission planning for future interstellar object investigations, demonstrating the value of maintaining public engagement with astronomical research. The interdisciplinary nature of Atlas studies showcases how modern astronomy integrates diverse scientific fields and analytical approaches to address complex questions that require broad expertise. The future discoveries. Atlas represents just the beginning of a new era in interstellar object studies that will dramatically expand our understanding of galactic structure, stellar evolution, and planetary system formation throughout our cosmic neighborhood. Next-generation survey systems will detect dozens of interstellar objects annually, creating opportunities for statistical studies that reveal population characteristics and formation mechanisms invisible in small samples. Dedicated spacecraft missions to intercept and study interstellar objects will provide detailed information impossible to obtain through remote observations, potentially revealing entirely unexpected characteristics and challenging current theoretical frameworks. The accumulating database of interstellar object properties will enable comparative studies that identify patterns and correlations across different galactic environments and evolutionary epochs. Advanced analytical techniques will extract increasingly detailed information from both current and future observations, revealing subtle signatures of formation conditions and evolutionary processes. The study of interstellar objects will evolve from characterizing individual curiosities to conducting comprehensive surveys that map the diversity of planetary formation outcomes throughout our galaxy. The scientific revolution. The discovery and study of interstellar objects like Atlas represents a paradigm shift in astronomy that provides direct access to materials from other stellar systems for the first time in human history. This revolution parallels other transformative developments in astronomy that have expanded our cosmic perspective, from the recognition that stars are distant suns to the discovery of exoplanets orbiting other stars. The ability to study materials from other stellar systems directly challenges theoretical models and provides observational tests that were previously impossible, potentially revolutionizing our understanding of planetary formation and stellar evolution. Future developments in interstellar object detection and characterization will accelerate this revolution, providing increasingly detailed information about cosmic environments throughout our galactic neighborhood. The implications extend beyond astronomy to fields including planetary science, astrobiology, and cosmology, creating interdisciplinary research opportunities that address fundamental questions about cosmic evolution. This scientific revolution will continue expanding human knowledge and perspective, providing direct connections to cosmic environments billions of years old and trillions of kilometers distant. The cosmic perspective. Atlas embodies the profound interconnectedness of cosmic systems, demonstrating how materials and information flow between stellar systems across vast distances and timescales that dwarf human experience. The recognition that we exist within a dynamic galactic ecosystem where objects regularly travel between star systems fundamentally alters our perspective on Earth's place in the cosmos and the nature of our cosmic environment. These interstellar visitors carry messages from distant worlds, preserving information about stellar environments and planetary formation processes that occurred when our galaxy was young and very different from its current state. The brief passage of Atlas through our solar system represents a fleeting connection across cosmic distances, linking our planetary system with ancient stellar environments through direct material exchange. Understanding these cosmic connections provides perspective on the vast scales of space and time that characterize our universe, while highlighting the remarkable capabilities of human science to decipher messages from the cosmic depths. The study of interstellar objects will continue expanding our cosmic perspective, revealing the complex relationships between stellar systems and the broader galactic environment in which we reside. The questions ahead. While Atlas has revealed remarkable insights into interstellar objects and galactic evolution, it has also raised profound questions that will drive astronomical research for decades to come. The mechanisms responsible for the unusual characteristics observed in Atlas remain poorly understood, requiring new theoretical frameworks and observational capabilities to resolve. These mysteries highlight gaps in our current understanding of cometary physics and interstellar processes. The true diversity of interstellar objects remains unknown, with each new detection potentially revealing characteristics that challenge existing theories and require new explanations. Future surveys will reveal whether Atlas represents a typical example or an unusual specimen. The frequency and characteristics of interstellar visitors provide information about galactic structure and evolution that complements other astronomical observations, but interpreting these data requires understanding of complex dynamical and evolutionary processes. The potential for detecting artificial objects among interstellar visitors raises profound questions about the prevalence of technological civilizations and our ability to recognize evidence of intelligence in astronomical observations. These questions will motivate continued research and technological development, driving advances in observational capabilities and theoretical understanding that benefit astronomy more broadly. The closing reflection. As we've journeyed together through the latest discoveries surrounding Atlas and unraveled the mystery of the so-called second comet, we've witnessed how a single cosmic visitor can transform our understanding of the universe around us. Tonight, whether you're drifting towards sleep as dawn approaches in Tokyo, finding comfort in these words during London's quiet evening hours, or perhaps discovering this exploration during an afternoon break in Sao Paulo, you've been part of something remarkable. The green transformation of Atlas, captured during September's lunar eclipse, represents more than just a change in colour. It embodies the dynamic nature of our cosmic environment, where ancient materials from distant star systems continue evolving and revealing secrets as they encounter new environments. The rapid brightening that surprised astronomers, the mysterious sunward glow that defies conventional physics, and the exponential increase in cyanide production all point to processes we're only beginning to understand. The confusion surrounding the so-called second massive comet illustrates how quickly information can transform in our connected world. While Comet Bernardinelli-Bernstein is indeed enormous and approaching our inner solar system, it won't arrive for years and poses no threat. The viral narratives that conflated multiple objects remind us of the importance of careful, patient science in an age of instant information. As Atlas races toward its October 30th perihelion, hidden behind the sun's glare from our earthbound perspective, spacecraft scattered throughout our solar system will witness its most dramatic moments. These robotic observers will capture data impossible to obtain from Earth, adding pieces to the puzzle of this cosmic messenger's true nature. What strikes me most profoundly about Atlas is how it embodies the interconnectedness of our galaxy. This ancient wanderer carries chemical signatures from stellar environments that existed when our cosmos was young, travelling for millions or perhaps billions of years through the void between stars before briefly illuminating our corner of the space. In studying this visitor, we're practicing a form of galactic archaeology, reading messages written in ice and rock by distant suns. Tonight, as you prepare for sleep, consider that somewhere above our atmosphere, telescopes are tracking this alien visitor as it hurtles toward its date with our sun. In the coming weeks, as Atlas emerges from solar conjunction and begins its long journey back to interstellar space, it will carry with it traces of our solar system's signature, potentially seeding distant regions of our galaxy with particles that once danced in Earth's magnetosphere. The questions raised by Atlas will outlive its brief passage through our cosmic neighbourhood. Each unusual characteristic challenges our understanding and pushes the boundaries of theoretical physics. As we await the next interstellar visitor, we can be certain that it too will surprise us, revealing new facets of the cosmic environment we're only beginning to explore. Until we meet again under these night skies, keep looking up, keep questioning, and remember that you're part of a universe far stranger and more wonderful than we ever dared imagine. Sweet dreams, fellow cosmic travellers. If tonight's exploration has sparked your curiosity about the ongoing mysteries of Atlas, I encourage you to share your thoughts in the comments below. What aspect of this interstellar visitor intrigues you most? Are you planning to observe the comet's emergence from solar conjunction in November? Your engagement helps build a community of midnight science enthusiasts who find wonder in the cosmos. Don't forget to subscribe for more deep dives into the universe's most fascinating mysteries, and ring that notification bell so you'll be among the first to know when new discoveries emerge from the cosmic depths. The universe is vast, full of secrets waiting to be discovered, and together we'll continue exploring them, one gentle night at a time.